Oh no, we're gonna rock down to
Electric Avenue.
and then we'll take it higher. Oh, we're gonna rock.
All right, let's get to work here. Little review from electricity from last week's work. Um, we learned that current is the flow of the charged particles in a circuit, and voltage is kind of the force moving them to flow. The voltage is also related to the energy, right? So the more volts, the more push you're going to have. A lot of you put that down in your lab. Also, they're bringing the energy to the light bulb or to any elements in the circuit. And resistance is kind of the electrical version of friction. I think it's somebody put that in their lab, and I think that's a great analogy here. It resists the change to that flow. So the more resistance, kind of the slower the things are going to move, just like friction. And the units of resistance are ohms. Voltage is stored in a battery. We also get it out of our wall outlet, and we'll learn that later, probably next week. But when we're looking at batteries, there's a chemical reaction going on inside the battery that's providing charged energetic electrons, and they go kind of from the positive, they go from the negative side of the battery to the positive side of the battery. There's just some different electrochemical reactions going on, and different elements are exchanging electrons. Not really what we need to learn here. But when this chemical reaction runs out of chemicals, then the battery dies and you get a new one. Unless you have a rechargeable battery, then you can charge it back up again. And but that's a special kind of chemistry. So these batteries here that we have on the right are usually AA, triple A's. These D cells are usually 1.5 volts. So that's the amount of energy they can bring. These bigger ones just have the ability to provide those volts faster and for a longer period of time. This car battery is 12 volts, but it can provide a lot of current and it can provide a lot more power. We're going to learn about power. And let me see, your iPhone battery is somewhere around 4.7 volts. But a rechargeable, thank goodness. So we'd be throwing out our iPhones every couple of days. Or carrying around giant battery packs like the one in our car just so that we can FaceTime with each other. Resistors, like our light bulb, we can also look at them with this funny little picture here. That's what you might see in a circuit, and this lab has those over here as well. This resistor will do the same thing as a light bulb in the circuit, but we won't be able to see the effect because we don't see it glow. So I like to use a light bulb for these labs. Good conductors have low resistance, and bad conductors have high resistance. So if we kind of open that up, we can see air is a very bad conductor. So there's a lot of resistance here, infinite resistance. So we're not getting any current going through this gap right here. And I know a lot of you tried different things to try these different types of materials, and you all kind of saw that the ones with metals are better conductors. If we look at a light bulb, you see this little glowy thing here. That's the resistance part. And it takes a lot for the electricity to kind of go through. There's a lot of push to get that through here. And as that electricity goes to the light bulb, it vibrates the atoms in the filament, and the electrons jump around their energy states. We give off infrared energy, we give off light, we give off heat, all because the electrons are changing energy states, but that's chemistry. So let's go back to circuits. Let's check this voltage. Let's make it 10 volts. And let's make this resistor maybe, let's make this resistor 5 ohms. So now we've got 5 ohms of resistance here, and we've got 10 volts, and we can do some math to figure out the current. And as you noticed, as the resistance goes down, you can see the current goes up. So there's an inverse relationship there. As the resistance goes down, the current goes up. Or I could also If the voltage goes up, the current goes up too, right? So you can see the current flowing faster and faster. So there's some math we can do here, and it's a very straightforward formula. So let's go back to 10 volts, and we have 5 ohms here. And we have a relationship called Ohm's law. It relates current, voltage, and resistance. And the equation is that the voltage equals the current times the resistance. Just three variables in this equation. So volt equals current times resistance. You can also rewrite this in a different way. That current is voltage over resistance. And I prefer this version, but you can use either one. It's the same equation. You see, if you multiply both sides by R, you're going to get V. This R is going to cancel out. You're going to get V equals IR. But it's the same equation as we see on this page. It's just bringing the R to the other side. But I like to say that the current is the voltage over the resistance, so that if the voltage goes up, the current goes up. And if the resistance goes up, the current goes down. So how does that work in our homes? Well, things that need a lot of current are going to have a low resistance, like a toaster or a hair dryer. They need a lot of current to generate that heat. So those devices are going to have a lower resistance than, let's say, an electric clock or a light bulb. Can't think of anything right now. But things that generate a lot of heat have low resistance, and things that are just, kind of like a clock or a radio, those don't need a lot of energy. They don't generate a lot of heat. So those typically have much higher resistances, and they use much less current. Take a snapshot here. All right, so let's try a little math problem here. Here's a problem. A light bulb has a resistance of 5 ohms. Let me see if we have that here, and has a maximum current of 10 amps. So let's see if we want to put 10 amp a meter here, 10 amps, right? So right now we have 2. So how much voltage could I put in this battery or in this power supply to get that to be 10 amps? And bulbs do break if you crank them up too high. But if I want to have 10 amps, so why do I have 2 amps here? Where I have a voltage of 10 and a resistance of 5. And if I go back, I have current is 10 over 5, which will be 2. But if I want to say, well, what voltage do I need to give me 10 amps? Well, voltage is going to be 10 amps times 5, 50 volts. So let's see if that's works. Let me see if that works. Can we get to 50 amps here? We can get to 50. If I get to 50 amps here, well, that's frustrating to watch. See, now I have 10 amps. So 50 equals 10 times 5. Now, eventually, if I crank this voltage up too much, and this can happen in our homes, and fortunately, this doesn't happen in our homes, but if we crank this up too much, we're going to learn this later. Oh, look at that, there's a fire. So if the current gets too much, and in this case, you see it's kind of 17 amps, everything catches on fire. And we're going to learn next week how we prevent that in our homes. But let's go back here. So we've solved that very straightforward math problem. And this is some things we're going to do in the first part of the lab where we're just uh, demonstrating Ohm's law. I've set up this circuit here to represent what's in this PowerPoint on the right. And I've built what we call a series circuit. And these 3 bulbs are in a loop in the same circle or the same circuit. And we call them that they're in series. And part of the lab is to understand how things work in this series circuit in terms of how much volts and current do each of these bulbs get when they're hooked up this way. And I just want to demonstrate this to you, and then I'm going to let you run the lab and figure out how to do that. But I want to show you some of the tools here. So we know I showed you the current meter, and right now there's no current flowing because the switch is closed. If I close the switch, I get that. And you don't need to put a switch in your lab. This is just for me for demonstration purposes. But I've got this light bulb at 30 volts, and maybe I'll change this resistor to 10 ohms, 10 ohms, and 10 ohms. Oh, that one's 5. So let's make this go to 10. Okay, so each of these are the same type of bulb right now. That's the first part of the lab. And we're going to do some math has to figure out what is the current here, what is the current here, what is the current here, what is the current here. And then in the second part of the lab, of the series lab, we're going to change one of these resistors to 5 ohms, which we can do just by clicking on the bulb and changing the arrow. And then we're going to check the current here, 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 and here. The lab also asks us to check the voltage, and you can grab this voltmeter and you can put it around this bulb like that. And if I close this, you can see that's measuring 12 volts. So this, when we put it around this bulb, we can see that bulb is using up 12 volts. That's the terminology that we use. If we want to check the voltage on this bulb, I just put these little probes around that, and that one's using up 6. And I can also double check my battery, and I can say, oh, that's a 30 volts. So the voltage we're going to measure kind of going around the device that we care about. The current is kind of like checking the flow, so we need to put that in the loop or just check what's going on there, how many electrons are moving in a certain period of time. So this is a series circuit, and I'm going to see if you can figure out some of the relationships in a series circuit. And the final part of the lab, or it could be the third lab, is looking at something called parallel circuits, which is a different way to hook up light bulbs. And we're only going to use 2 in this case, just because it gets a little cumbersome with this simulation. But they're not all on the same loop. You see over here, this is like one loop, and this is one loop. So I can draw a loop from the battery here, and I can draw a loop from the battery here. And if I close up the circuit with this switch, well, look at that. That's amazing. There's a lot of bulbs going on there. Let me pull this one out here. And what I'm going to ask you to do is look at the different numbers, the different resistors, the different flows, things like that, to see if you can come up with what's going on here. I just want to show you one more control. I'm just going to close the switch. If I want to disconnect a light bulb or disconnect a part of the circuit, if I just click on this circle and hit the scissors, that's open, right? So now you can see nothing's coming this way because I've hit the scissors on that junction. It just means cut it open, and then I've got that. So that's how these tools work. If you have any questions on how they work, let me know. Remember, we can use these volt probes to kind of go around the object to see how much energy this guy is using. And I can put the current meter to see what's the rate of charge or how fast the charge is flowing. So I hope this is a good introduction to how this lab works. And let me know if you have any questions. And the reason we're doing this, again, we're going to move into kind of this basic setup here to try to understand how electricity works in our homes, how we provide safeguards in our homes, and in general, how, probably one of the most important inventions that we have allows us to live and use all the tools that we have in our homes, from everything from heating to music to light to getting places. So enjoy the week. Talk to you soon.